Swayam Prabha. Digital India. Educated India.
How about power absorption? In the system. Since there is friction in the system, obviously when the oscillator is moving, it is losing power due to heat, and that power is supplied due to friction, and that power is supplied by the force being applied. Now, power loss due to friction is going to be the force minus BV times V, which is equal to minus B x dot square. Let us put that in. So, power loss as a function of time is going to be minus B, which is nothing but m gamma. Remember, gamma was defined as B over m, times x dot square, which is f over m times omega with a minus sign, divided by square root of omega naught square minus omega square square plus gamma square omega square sine of omega t minus phi square. This is the velocity square. When I open the bracket up, I find that P is going to be equal to f square gamma omega square over m omega 0 square minus omega square square plus gamma square omega square sine square omega t minus phi. So, power really fluctuates. If I were to calculate how much power is lost, average power over one cycle, that means I integrate the power 0 to t and divide by t. So, on an average per second, how much power is being lost? Sine square omega t minus phi averaged over a cycle is always a half. Recall RMS value from AC circuits in your 12th. So, average power comes out to be f square gamma omega square over 2m omega naught square minus omega square square plus gamma square omega square. This is the average power loss in the system. Is it equal to the power supplied? It should be. Let us calculate that. Power supplied is going to be equal to the force applied times the velocity, and this is going to be equal to f cosine of omega t. Remember, force is changing with time. Let me write this f t. Velocity is minus omega f over m divided by omega naught square minus omega square square plus gamma square omega square 1/2 times sine of omega t minus phi, and this can be written as minus omega f square divided by m naught square minus omega square square plus gamma square omega square raised to 1/2. Open this up, you get cosine omega t sine omega t cosine phi minus cosine square omega t sine of phi. So, power being supplied is fluctuating, and when I calculate average power, that means I integrate it with time t and divide by t. This term is sine 2 omega t and it is going to give me 0. Cosine square omega t integrated over a cycle is going to give me 1/2, and this minus sign takes care of this minus sign, and therefore average power supplied is going to come out to be f square omega over m omega naught square minus omega square plus gamma square omega square raised to 1/2 sine of phi. Sine of phi, you recall, is gamma omega divided by this quantity. Therefore, this comes out to be f square gamma omega square 1/2 because of cosine square omega t being averaged divided by 2m omega naught square minus omega square plus gamma square omega square raised to 1/2, which is exactly the same as we obtained earlier by calculating the power being lost. So, power supplied is equal to power lost, as must be the case for the steady state motion to sustain itself. So, we find that P average supplied or lost is equal to f square gamma omega square over 2m omega naught square minus omega square plus gamma square omega square. Let us see how this power changes as I change the applied frequency. And again considering light damping, you will see that this looks something like this, where the maximum is obtained at omega equal to omega 0. So, you see, when there is resonance, that means the amplitude is maximum, the power that I need to supply to sustain the motion or the heat that is generated in the system due to friction is also maximum. And at omega equals omega naught plus gamma over 2 and omega equals omega naught minus gamma over 2, the power becomes half of the peak power. So, suppose this is P maximum. At these two frequencies, this becomes P maximum divided by 2. So, this width, the frequency width is gamma. This is known as width, full width at half maximum. Let me recap. When I plot for light damping P average versus frequency, P max is at omega equal to omega 0 and the power absorbed or power supplied falls by half at frequencies omega naught minus gamma over 2 and omega naught plus gamma over 2. This is known as the width of power absorption curve. So, width of power curve is gamma, resonance frequency is omega 0. You see right away that the quality factor is also related to the resonance frequency and the full width at half maximum. This is another way of looking quality factor Q that we had introduced in the previous lecture. So far, we have looked at steady state solution, but recall that the general solution x t is e raised to minus gamma over 2 t c cosine of omega 1 t because damped oscillator sine of omega 1 t plus x steady state. So, this factor really makes the solution, homogeneous solution, go down for times greater than 2 over gamma. For times less than say 1 over gamma, we are going to have significant contribution from this solution also. So, in general, for such times we are going to have two parts of the solution, one part which is the decaying part, the other part which is the steady state part, and the total solution is the sum of the two. Let me show it here. The total solution may look something like this. And then finally, it goes to the steady state solution. These are known as transients because they exist for a short time of the order of 1 over gamma. However, what you notice, the transients could give you a very haphazard motion. Take an oscillator, force it with a certain frequency, and you will see initially it's moving back and forth in no regular pattern, and those are the transients. After some time, these transients or the homogeneous part dies down, and what you see is the steady state solution. This is one thing that I thought I should mention. Finally, I would like to state that I could also apply more than one force on the system. Not only that, their frequencies could be different, phases could be different. When I say phases could be different, I mean when one force is maximum, other force need not be maximum at that time. So, what would be the motion in general? As I said in the beginning of the lecture, a general periodic force can be a sum of many different frequencies. So, let us say if I have applied two forces, this should be B, K, X, two forces F1 cosine of omega 1 t plus alpha 1, where alpha 1 is a phase, plus F2 cosine of omega 2 t plus beta. So, there are two different phases, alpha and beta, two different forces. What would be the general motion? Recall that this is a linear equation, and therefore, principle of superposition holds. If I were to look at only steady state solution, x is steady state, it would be solution corresponding to F1 plus solution corresponding to F2. This is because of the superposition. Principle that tells me that any linear equation, for any linear equation, the sum of the two solutions is also a solution. You can substitute it back and see, because the equation, when you substitute m x f1 double dot plus b x f1 dot plus k x f1 is equal to f1 cosine omega 1 t plus alpha 1 is satisfied, and for 2 f2 cosine omega 2 t plus beta is satisfied. Therefore, the sum satisfies on the right hand side, this being added. I would like you to solve this problem, particularly see the case when omega 1 is nearly equal to omega 2. See what the sum of these two solutions looks like. What you will observe is that in this case, when omega 1 is nearly equal to omega 2, and let us take alpha to be equal to beta to be 0, you will see that the solution would be of this form. So, the amplitude would be varying with time, and the frequency of oscillation would be roughly equal to omega 1 plus omega 2 over 2, and this frequency of change of amplitude will be omega 1 minus omega 2 over 2. I would like you to do this exercise yourself by adding the two solutions. So, this is like the phenomena of beats. So, let us conclude our lectures on harmonic oscillator. These are some basic ideas about harmonic oscillators. You can obviously, this is such a robust model that you can keep doing more and more and more. We have looked at freely oscillating system. We have also looked at damped oscillations in the regime of heavy, critical and light damping. We have also looked at forced oscillations, resonance and power absorption of a damped force oscillation. I have also indicated to you how to get solutions for more than one force with different frequencies. What I have not covered is how to do this using complex algebra and many other terminologies like response functions and things like those, but given these basics, I am sure you will be able to cover them on your own.